Very, very important that everybody already knows, but it's my job to remind you that something amazing happened almost 30 years ago. And the something amazing is that we discovered that neutrino masses are not zero. They are approximately equal to zero. They're super tiny, but nonetheless, we're very, very sure that they're not zero. And if you don't think about neutrinos on a daily basis, you may be less than impressed by this fact, because you can tell yourself, all the other particles have mass except the photon. Why should I care that neutrinos have a non-zero mass? And the reason is, in spite of what Carlos told us yesterday, this is the only most robust evidence we have that the Standard Model is wrong. So there's something missing in the Standard Model of particle physics that allows the neutrinos to have mass. So this is what I want to remind you of, and I want to try to give you a sense of what that statement means. And I can see the clock here too, so I'll do that. So the one way you want to think about the statement that neutrinos are new physics is that if you look at the Standard Model of particle physics, and you look at the particle content of the model, and you want to give the neutrinos a non-zero mass, you have to add some new field. Okay, so that's something we know is absolutely true. There's no way of giving the neutrinos a mass without adding some new field. So that's exciting, that's new. And the question is, which field is that? And the answer is, we have absolutely no idea. We know that this new field could be a fermion, it could be a boson, it could have charge, or it could have no charge, it could be ridiculously heavy, or it could be super light. So I think that covers all the possible bases. So on the one hand, we know that there's something new out there. We're absolutely sure that there's some field we're missing, but we have absolutely no idea what this field is. What I like to mention is, if you look at particle physics today, there's a couple of other things that we also know the Standard Model doesn't explain. The most obvious one is the dark matter puzzle. And if you ask around, because we're all particle physicists, we're all going to tell you that dark matter is a new field, it's a new particle. I think we should always remind ourselves we have no idea if that statement is correct, but because we're particle physicists, we're very sure it's some new particle. And then there's a few other things about particle physics that we also don't know, but they're all sort of cosmology and astrophysics related, and cosmology and astrophysics are very hard, so I'm not going to talk about that. So we have a problem. And I want to, before I tell you a little bit more, I want to give you a sense of why there's so many ways of giving the neutrinos a mass. So here I have a summary that hopefully will be helpful for people who don't talk about particle physics on the different ways in which neutrinos get a mass and why that's related to completely different new physics ideas. So you want to give the neutrinos a mass. We know that mass has to come from electroweak symmetry breaking, and that's also true of the neutrinos. Whatever's happening with neutrinos, they get their mass from electroweak symmetry breaking. Now, what's interesting is that the neutrinos have choices, which is something that the other fermions don't necessarily have, and the choices can be broken down into three kinds of choices. This is very broadly defined, and it's completely arbitrary. You don't have to agree with me, but I'm giving the talk, so I'll tell you what the choices are. So the first one is that maybe the neutrinos get a mass just like everybody else. They talk to the Higgs boson, the Higgs gets a VEV, the neutrinos get a mass, and since the masses are very small, they have a tiny Yukawa coupling. And you can say, okay, I believe that, that's probably what's going on, why are you bugging me with all these neutrino experiments? And this has some non-trivial consequences that I won't talk about in any detail because I don't have time, but one thing that's very interesting is if the neutrinos are what we call Dirac fermions, then lepton number has to be an exact symmetry of nature. If you're a theorist, you know what that means. If you're an experimentalist, I'll tell you this is a very, very non-trivial statement that your string theory friends will tell you is not even allowed. And we believe our string theory friends. Okay. Another possibility is that the neutrinos get a mass from a different Higgs. People like that idea because the neutrino masses are very different from everybody else's mass. And maybe having the neutrinos get a mass from a different Higgs is interesting because it explains why the neutrino masses are so small, and at the same time it tells you that you have a new Higgs. There's a third idea, which is that maybe the neutrinos get a mass from another source of mass. We know that the Higgs boson is a source of mass. Maybe there's a new source of mass out there, and the neutrino masses are a consequence of a marriage of these two different sources of mass. This is the most complicated idea. The simplest version of that is the seesaw mechanism that I assume many of you have heard about. And of course, because it's the more complicated idea, that's the idea everybody likes. So if you ask around, your theory friends will tell you this is exactly what's going on. And of course, in order to solve this problem, we need more experimental data. So I want to give you a flavor of, if you like the third idea, you can now ask, what is this new source of mass? And this new source of mass is anywhere between the electron volt scale and the ZeV scale, which is around the gut scale, and everything in between. So all of these are possibilities for the new source of mass. And the way that we look for that depends on what that mass scale might be. So the kinds of experiments that you should care about will range from oscillation experiments to meson decay experiments to high energy collider and other things that people like to talk about. And here I also highlighted other kinds of interesting things that people care about that may have something to do with neutrino physics. And this is just to give you a sense of if there is a new mass scale out there, the neutrinos are not going to tell you by themselves what that scale is. We need more experimental data. So how do we solve this neutrino mass puzzle? We kind of have to look everywhere. And here is a very long list of the types of experiments that you should be paying attention to if you're interested in neutrino masses. And they range from searches for double beta decay, to collider physics, to astrophysics and cosmology. And we already heard a little bit about that yesterday from Scott's talk, and also from Mostafa's talk. So fortunately, there are going to be talks that will talk about all of this. So that means that this is kind of important, and many of these talks are following my talk today. Now, I have to make choices because I have 17 minutes, and I'm mostly going to talk about things that are related to neutrino oscillations. And you can tell you, why would you do that? First of all, because I have limited time and I have to pick something. But I do want to remind you of something, which is if you want to study neutrino masses, which is what I want to try to learn about, it is useful to remind yourself that we've only seen neutrino masses in neutrino oscillation experiments. We've tried with other kinds of experiments. Actually, we've been trying for 100 years. You know, when Fermi wrote down the Fermi interaction, the next thing he did was to say, by the way, if the neutrinos have a mass, you should see some change in the beta spectrum. And that was around 1930-something. And that's approximately 100 years ago. And in spite of that, we've only seen neutrino masses in neutrino oscillation experiments. So it stands to reason that if you want to learn about neutrino masses, you should probably do neutrino oscillation experiments. That's not a scientific statement. It is a, it sounds right statement, but it feels like we should be doing more neutrino oscillation experiments to learn more about neutrino masses. And we don't know if it's going to work out. But you only find out when you get your job done, and then you see what happens. So I want to give you a sense of what we know about neutrino oscillations, because I want to give you a sense of what we don't know about neutrino oscillations that tells us why we do these neutrino oscillation experiments. And I want to do it from a bird's eye view, and I don't want to write down any equations for now. And if you ask, what have we done with neutrino oscillations, the answer is a lot. So we know that there are two oscillation lengths, a big one and a short one, and we've seen oscillations related to both of those. We know that solar neutrinos oscillate into some combination of nu mu and nu tau with the long oscillation length. We know that reactor antineutrinos oscillate into some combination of nu mu and nu tau with both oscillation lengths, which is very impressive. And of course, the Juno experiment now is getting to the point where they can see both oscillation lengths at the same time, which is really amazing. We've studied atmospheric neutrinos, and we know that nu mu's and nu mu bars oscillate probably into nu taus with the short oscillation length. We've also figured out that the nu mu's and the nu mu bars can oscillate into electron neutrinos with a very small probability, and also with the short oscillation length. And we've also done that with accelerators. And I didn't read them correctly, but you got the message. So I can tell you what we don't know. So if you don't believe any models, there are many things we have absolutely no idea in terms of oscillations. We don't know what the nu taus do. because we're not good at making new tau beams. We've actually never seen the new mu oscillate with the long oscillation length. We're pretty sure they know how to do it, but we haven't really seen it in any unambiguous way. We don't know if neutrinos and antineutrinos oscillate the same, that is CP violation. We also have no idea if a T invariance is violated. So if you study like nu mu to nu e oscillations and you compare it with nu e to nu mu oscillations, do you get the same answer? And by the way, another interesting question is we don't know how much the nu e oscillates into nu mu relative to nu tau. When I say we don't know, it means we've never measured it. We do have a theory, and that's the theory of neutrino oscillations. The idea is very simple. You've heard it before. You can define neutrinos with a well-defined mass, and these are the neutrinos with flavor that you learned about in your textbooks. And these two bases are related by some CKM-like matrix that we call the lepton mixing matrix, or sometimes the PM&S matrix. And this is parameterized by the masses of these states and the entries in this mixing matrix. And with this model, we can take all of the data and we can fit all of it. And we can do a great job. So hopefully I got the numbers right. So we can measure all of the parameters of neutrino oscillations. And after about 30 years, which is when we knew that neutrino oscillations were a thing we should worry about, we've actually done a ridiculously good job. You know, we can measure these oscillation frequencies at the percent level. Again, if you're old, this sounds absolutely crazy. I mean, if you remember, we were happy when we measured this at the order of magnitude level, and that was only, I don't know, 25 years ago. We can measure the mixing parameters really, really well, and then there's some things we haven't measured yet. So that's really exciting. I am skipping some stuff that we don't understand from experiment because we think it's not important, but there's going to be a whole talk on that, so you should pay attention to that talk because they'll tell you what are the things that are missing in terms of data, which is the short baseline anomalies. So if you look at the oscillations question, you can ask yourself, what is it that we haven't done yet if you believe this model is correct? And here's a list of things that we haven't measured. One is what's called the neutrino mass ordering, which I'm not explaining because I assume you've heard this many, many times. And if you haven't, the next talk will tell you about it. But, so we don't know what's called the neutrino mass ordering, which is we don't know if the neutrino masses look like this or if the neutrino masses look like that. We don't know if CP is violated yet. The data point to probably yes. We don't know what's called the octant question. If you don't know what that is, don't worry about it. I won't tell you any more about that. We don't know about the pictures. And these answers, these are things that we know we can measure, and we can only measure that with neutrino oscillation experiments. I will say, if you've listened to enough neutrino talks and the talk got to this point, you will be underwhelmed because you say, look, we're doing all these experiments just to measure like a 2.5 numbers. That sounds a little excessive. And of course, that's not why we do these experiments. I think that measuring these parameters is really interesting, but that's not the point. The point is we want to know if this idea, if this model is correct. So we don't want to measure stuff, we want to test if this formalism is right. And as a reminder, we want to do this in the neutrino sector. So for those in the audience who know what this is, it requires no introduction, but this is the same idea for quark mixing. So for quark mixing, we've been doing experiments for a long time. And I want to remind you of one thing, which is this is a very colorful plot. It's actually very old. There's an updated version of that maybe somebody will show today or tomorrow. And every colorful color here is a measurement from some experiment. And they're all trying to measure 2 parameters. And that feels like a waste of energy. You know, we want to measure 2 parameters. Why do we do half a dozen experiments? And the reason is, we want to know if all of these experiments agree with one another. Because if they don't agree, it means that our model is wrong. It's a great way of checking models. Now, sadly, they all agree. They all meet over here at this point. And if you look at the updated version of that, they all agree at a smaller version of this point. But we want to do something similar to that with neutrinos. And the challenge with neutrinos is that the number of measurements we can make is a lot smaller. So it's a different kind of challenge, but it's qualitatively the same. So here's a reminder of the mixing matrix that I showed you before. And this is just to tell you, even though I told you that we can measure all of these parameters at the percent level, we can only do that because we're assuming that the model is right. If you don't believe in the model, the amount of stuff that we've measured about this matrix is actually relatively limited. First of all, we only measured these elements and these elements. We've never measured any of those. They're all inferred by unitarity of the matrix. So if you're in the business of being agnostic and measuring everything, we have a long way to go. So this is a picture of the unitarity triangle in the neutrino sector today. The way you want to look at this is you want to look at the biggest possible contour there, and that's where the data lie today, if you make the fewest number of assumptions. And the smaller contours here is where we might be after Dune and Hyper-K run. And we're going to learn about this unitarity triangle, and we're going to shrink it a lot. And right now, we know virtually nothing. Now, I want to show you some nice plots that we saw from the NOVA collaboration a couple of days ago. This is a way of stress testing the model, which is we can look at, let's say, new E appearance in NOVA, and the data prefer this banana-shaped thing here in this parameter space. We can look at new mu data in NOVA, and you get this nice blue region here. And they actually overlap, which is nice. That means the model is working. You should be underimpressed because it's not difficult for them to overlap. The diabase measurement is here, and it also overlaps really well. And in the future, some theorists have thought about this, and we would get to a world where if everything overlaps, we're going to be living in this tiny world. And then you can ask yourself, is it possible that they will not overlap? And the answer is yes, but it's actually very interesting, and it tells you why doing oscillation experiments is important. So this is a hypothetical scenario where we could be if we ran Dune and Hyper-K data. And again, these are different measurements of different oscillation signals. And you notice that there's no region here in this plane where all the different measurements agree. And if we lived in that world, that would be super exciting. And I do want to highlight that this statement is only correct if we look at tau appearance in the Dune experiment, which is really hard to do, and it's not a very good measurement. It would be this green region here, but the green region is the thing that's telling us that if we lived in this world, unitarity is violated. So another question that people often ask, what if we don't run into any surprises? Why do we care about measuring these mixing parameters at the percent level? And some people get excited about flavor models. I'm not going to tell you about any flavor models, but I'll give you a sense of what these flavor models do, which is what they do is you have a bunch of parameters, and the flavor model tells you that these parameters are correlated. So the question is, I want to do precision measurements because I want to test correlations. And to test correlations, you're at the mercy of the thing that you measure the least well, so that means you'd like to measure everything well. Another thing that people like to do with flavor models is to relate the quark sector to the neutrino sector. So again, there'll be some function of neutrino mixing stuff with quark mixing stuff, and that tells you that the precision with which you can test those hypotheses is probably going to be governed by the thing that you measure the least well, which means that you'd like to measure a mixing parameter as well. Ironically, the thing that we know the least well is what's called the theta 2-3 mixing angle, which is the first one that we measured in 1998 with the Super K results. That one turns out to be hard to measure because it's in the wrong region of parameter space. And I'm going to skip this one. So for the last 5 minutes, I'm going to tell you about the other possibility, which is, imagine we do run into some interesting inconsistencies in our measurements. So you're allowed to ask yourself, is it possible that we'll do all these neutrino experiments and run into something interesting? Or what could that something interesting be? And of course, that's what theorists do. So that's what I do sometimes. And the question is, what kind of new physics can we run into in the neutrino sector that we haven't seen yet? And I'll give you a list just to give you a sense of the types of new physics models that people think about. And it's nice to think about these a little bit because sometimes they're very different from the kinds of things that people worry about with, say, collider experiments. So what could happen? For example, there might be more neutrino states. So unlike the charged fermions, adding neutrino states is kind of cheap. It's very easy to add a lot of new neutrinos to your model and not screw up anything. The model works perfectly fine. Everybody's happy. But if we have new neutrino states, it means that our mixing matrix is not a 3 by 3 matrix, it's a big matrix. So clearly the 3 by 3 piece of that is not going to be unitary. And of course, if you add new neutrino states, depending on their masses, you also add new oscillation frequencies. So these are things you can see in your experiment. Maybe the neutrinos have new interactions. The neutrinos only interact via the weak interactions. So if there's some other interaction out there that's a little bit weaker than the weak interactions, the neutrinos are a really good place to see it. And it turns out that new weak-like interactions can change how neutrinos oscillate as well, through matter effects, which I'm not going to talk about because I'm running out of time. Of course, neutrinos can have other fun properties. Neutrinos can decay. And you can ask, what would a neutrino decay into? The answer is into another neutrino that's lighter than it. And a photon, maybe, if you like photons. And of course, the neutrinos can also have a magnetic moment. What's interesting is, because the neutrino masses are not zero, we know for sure that the neutrinos decay. And we know for sure that they have a magnetic moment. On the other hand, if you take the standard model, you can calculate those things like the lifetime and the magnetic moment. And the lifetime is like 10 to the 40 years, which is a big number. So we don't have to worry about it. None of the neutrinos are going anywhere. But if you have new physics, that can change a lot. And that's something that people look for. And of course, neutrino oscillations are exciting because it's quantum mechanics. So if quantum mechanics, in many quotes, is wrong, the neutrinos might tell us about it. We like quantum mechanics. We don't think it's wrong, but we can test it. So I'm just going to tell you one story that you can talk about and measure with neutrinos, which is, so we talk about mixing angles and masses. And mixing angles are really just couplings. We call them mixing angles, but they're just couplings. And couplings can run in the renormalization group sense. So one question is, can the neutrino couplings run? The answer is, of course, yes. The answer is, can they run by a reasonable amount? And then the answer is yes if you ask a theorist, because we can write down a model that does that. And if you have your parameters run, it turns out that neutrino experiments usually have two scales. One is the scale where the neutrino is produced. So that talks to couplings at a certain q squared. The other one is the scale where the neutrinos are detected, which has a different q squared, which means in principle we have different mixing angles at different parts of our experiment. And that leads to interesting physics. And you can now ask, can I write down a model where the angles run a lot? The answer is yes, because we're theorists, we can do whatever we want. And here it says that you can see that I can write down a model where the mixing parameters can run by 10, 20, 30%. Now you can ask me, are these nice models? Are these models that do anything useful? And I'm not going to answer that. But that means that the effect is there, and it's something that experiments could measure, and it would be super exciting, and it would basically tell us that there are new states around the MEV scale. I'm going to skip this case because I'm running out of time. The last thing I want to remind people of is, if you don't care about neutrino physics at all, you should pay attention to the fact that neutrino experiments are interesting. And they're interesting in lots of different ways, just the experiments themselves. They have super duper ridiculously intense beams. They are really big. It's a gigantic detector because neutrino interactions are so weak. The oscillation experiments, the oscillations themselves are quantum mechanics that's coherent over thousands of kilometers. And we have all these weak processes. So that means we can look for a lot of different stuff. And for example, just as a simple example, neutrino beams are produced by pion and pi zero decays. So every time a pi plus decay,
Okay.
if it decays into some new
Test.
state.
Hello?
Okay, was that me? No, okay, I'll just keep going. If they decay into some different states, like a heavy neutrino or a dark photon or dark matter, these are things that could show up in your detector. And even if these couplings are small, we have a lot of pions. And even if these things don't interact very much, we have a really big detector here. So we're kind of covered. And we even have a long distance here, so we can get rid of backgrounds and we can look for things that live very long. Okay, so I have 0 time. I'm going to skip things that you can do with this, and I'm going to conclude. Okay, good. So that worked out well. And I'm going to eat into the extra minutes that I found out I don't have, and just to give you a sense of where we are. So first of all, the most important thing is we found new physics in the neutrino sector, about 30 years ago, we have absolutely no idea what that new physics is. But it's a well-posed question. We know it's there. We know neutrino masses are super small. And when you talk to theorists, that's the problem they're trying to address. I didn't talk about the fact that neutrino mixing is weird, but that's the other thing that we care about. I think the other message is, in order to make progress in this field, we need more experiments, which is exciting because we have a whole bunch of new experiments coming online, and we're going to hear about them in the remainder of today and a lot of tomorrow as well. I try to give you a sense of why measuring neutrino oscillations is very important, because there could be a lot of information hiding there. And there's still a lot of work to be done, both on the theory side and the experimental side, to kind of make progress of the type that leads to our understanding of the neutrino sector being similar to our understanding of the quark sector. And of course, there's always a lot of room for surprises when you're doing these quantum mechanics experiments. One thing I like to say, which I've already said, but I'll say it, it'll be the last thing I'll say, it's, again, if you don't think about neutrino oscillations very much, you should pause and convince yourself that it's absolutely amazing. Because we have this quantum mechanical object that is produced by some very mundane thing, like beta decay, which is really messy, right? Beta decay, a bunch of stuff is happening, but you get this coherent, pure quantum state that remains coherent for thousands of kilometers, which is ridiculous. Again, the other joke is, you probably have atomic physics friends. You should remind them that they're very proud of their coherent states that live like a millimeter or sometimes like a centimeter. We have coherent states that live 1,000 kilometers. And that must be good for lots of things that we haven't run into before. Okay, so I'll stop here. Thank you.
Thank you, André. So, time for a quick question. Here, please.
Well, thank you very much for your very interesting talk. I have looked at your transparencies in advance, and I haven't seen any mentioning about magnetic moment. Now you have mentioned it,
yes.
But I have another question to you. And what about the neutrino melee charge that indeed also possesses new challenges theoretically and a lot of new possibilities?
Yeah.
Thank you.
Yeah, so this falls into the category of other properties that neutrinos can have. I mentioned the ones that are very straightforward. The magnetic moment, for example. Another one which is very exciting is the electric dipole moment, which doesn't have to be a lot smaller than the magnetic dipole moment, which in itself is kind of interesting. But of course, you can ask the questions about all these different kinds of electromagnetic form factors, and you can even ask if the neutrino has a super tiny charge. And there are lots of experiments that are very good at trying to answer that question, and people have been spending time on that. And I'm happy to chat about it later. Yeah.
Question there?
Okay, thank you for your talk. I want to complement some of your list there, because also there is what is called very special relativity, which was proposed by Cornel Glashow in 2006. There you consider a subgroup of the Lorentz group, and that preserves all the properties of the standard model. You can prove renormalizability, and you have chiral neutrinos without introducing extra particles. So that, I think, should be considered seriously now.
Okay, thank you.
Last question. There.
Very much for the very nice talk. You mentioned 3 possibilities for neutrinos to acquire mass, so coupling to the Higgs, coupling to an extra Higgs, or something like a seesaw mechanism. Could a type 2 seesaw be related to an extra Higgs?
Yeah, that's a very good question. That's a more technical question. In principle, if you look at the type 2 seesaw at face value, it feels like it's an extra Higgs. The problem with the, okay, very short answer. The issue with the type 2 seesaw is that it has some charged new particles as well. And because you guys have done so many collider experiments, these things have to be heavy. And because the new particle is heavy, and because you can't have a Goldstone boson, it means you need to explicitly break lepton number. And that means there is a new Higgs which gets a VEV, but you can also think about it as integrating out some new heavy particle. So it falls into category number 3. Because you're not just using the weak scale, but you're using, there we go. But you're using a new mass scale as well, and this new mass scale plays a very important role in the story. So yes, it is a new Higgs that gets a VEV, but the parameter that you care about will be inversely proportional to some new mass scale, which is not related to the weak scale. So yeah, thanks for the question.
Thank you, Andre. So now we will have a talk about the neutrino properties from long baseline experiments. Stefan Dolan.
Okay. No, I'm okay. I think I'll be fine with this. So first of all, sorry, Andre, for accidentally interrupting part of his talk during the testing there. But first of all, thank you very much to the organizers for inviting me to be here. I'm really pleased to have the formidable challenge of telling you about the status and prospects of long baseline neutrino oscillation measurements in just 20 minutes. So let's get started. So what I want to be able to do is to first tell you a little bit about where we are today in terms of precision measurements from T2K and NOVA before showing how we're actually close to, within the PM&S framework of neutrino oscillations, getting to the end of it. But then I want to also echo the point that Andre made about saying that this is not the end, that Dune and Hyper-K form a complementary way of looking at physics beyond the standard model to what we've heard about from the Collider community. So let's get started, though, with just a quick reminder about how these experiments work. The basic idea is you create a neutrino beam and you measure it twice. So our neutrino beam is peaked at about 1 GeV, and the first time we measure it is at a near detector. We measure charge current interactions, so we look for those muons predominantly, and the spectra, the shape, and the normalization of our event rate is proportional to the neutrino cross-section, the neutrino flux, and detector effect. So it tells us about the unoscillated properties of the neutrino beam. The neutrinos then oscillate, sometimes even on a continental scale, many hundreds of kilometers from the near detector to the far detectors. Now, in order to maintain reasonable statistics, these far detectors have to be enormous. So they range from 10 kilotons up to the next generation having over 200 kilotons of material. And when the neutrinos arrive at the far detectors, we expect to see an oscillation. We'll expect to see an almost maximal disappearance of muon neutrinos and a small appearance of electron neutrinos. Now, most of the neutrinos go to taus, but our energies are a little bit too low to be able to make high statistics tau measurements, although it is part of the program for Dune, as Andre mentioned. Now here again, we measure event rates, and this time we've got two event rates we can really access, the muon and the electron event rates, and now you can see the formula there. Now the oscillation probabilities are there, so we can infer the muon neutrino survival or the electron neutrino appearance event rates. Now we can flip this whole experiment as well, flip our magnetic focusing horns, and then we can run this whole thing in anti-neutrino mode as well, giving us 4 oscillation probabilities that we can access in total. So what is it that we're actually trying to get at? Well, Andre covered most of this, so I'll go through it very quick. But we learned that, okay, the oscillations, they have a phase. The phase depends on the difference of the neutrino mass-state masses, and also characteristically on the ratio of the distance the neutrinos travel, L, over the neutrino energy, E. I'll show plots as L over E throughout this talk, and that is why neutrino oscillations evolve characteristically like that. Then the amplitude of the oscillation then depends on the PM&S mixing matrix element. So what are we sensitive to really in the long baseline experiments? So first of all, we're sensitive to the difference between we're sensitive to large mass splitting. You can see what I'm showing you here is the oscillation probabilities we're sensitive to. So top is muon neutrino survival, bottom is electron neutrino appearance, solid is neutrinos, dashed is antineutrinos. First of all, note the difference in scale. You're really working at an order of magnitude less signal in the bottom channel there. But what you can see is this mass splitting, it shifts the oscillation probability backwards and forwards. So that's what we're looking for. We can also measure the sign. This is resolving the mass ordering, as Andre mentioned. And you can see the main thing that this is doing is actually changing the electron to anti-electron neutrino appearance channel. So we're sensitive to the mass ordering like this. We're then sensitive to 2 of the mixing angles. Theta 2,3 controls the overall scale of the oscillation. You can see it's affecting both channels there. Whilst theta 1,3 is really telling us how much of the muon neutrino disappearance is going into electrons and how much is going into taus. So you see it's controlling our electron neutrino appearance event rate we can measure. And then finally, and maybe most famously for these experiments, we're of course sensitive to the CP violating phase as well. And you can see what this does is really change the relative ratio of the electron and the electron neutrino appearance to the anti-electron neutrino appearance. Now, what experiments are actually measuring this? Well, right now, it's T2K and NOVA. So T2K is a long baseline experiment in Japan. It's got about 300 kilometers of baseline. We've got a beam peaked at about 0.6 GeV, uses water Cherenkov detectors, and with about 23 kilotons. Its complement in the US is NOVA. NOVA uses a longer baseline, and since we want to keep L over E the same, so we keep our experiments at the first oscillation maximum, it's got a correspondingly higher neutrino energy as well that you can see. It uses liquid scintillator technology. Now, what I want you to see here is also in the statistics that we expect, you can see that our electron neutrino appearance statistics are quite a lot less than our muon neutrino survival statistics. That's expected from what I showed you before. But you can also see that in over 10 years of operation on the T2K side, these statistics are actually still relatively small. So these are statistically challenging measurements. Now, I actually do want to show you some of the data, though, here. And so you're seeing this is the event rate as a function of a reconstructed neutrino energy. And you can see that what you're seeing on the muon neutrino survival side is this dip. And this dip is really the oscillation, or tells you a lot about the oscillation. So the depth is telling us about theta 2-3, the position about the mass splitting. And then I can show you two of the electron neutrino and anti-electron neutrino appearance events that T2K has measured as well. The amplitude tells you about theta 1-3, and the difference between the two tell us about delta CP. So I talked about T2K, I talked about NOVA, but I can talk about T2K and NOVA together. I won't go through this plot in detail. I just want to tell you that these experiments have worked really quite hard to be able to produce a joint analysis between the two. This isn't easy because there are a lot of correlated systematic uncertainties to deal with here, but the overall story of it is that the measurements are very compatible and that they enhance sensitivities of each other by being combined. So then, this is great what we can do with those experiments, but we can go further as well if we can get a little help from our friends. And the first friend that I want to tell you about is Juno. Now, you'll hear much more about this, and the next speaker will cover all of the details, but I want to share with you the way it impacts long baseline measurements. So Juno now reports percent level constraints on the mass splitting itself. And it does this by measuring electron neutrino survival. I already told you that we can do this using muon neutrino survival as well, and again, we measured the mass splitting. Now, it turns out when we report a mass splitting, we can report it assuming a particular mass ordering. So we can assume normal ordering, inverted ordering, and we'll get a slightly different value depending on which one we assume. Now, if we set up our measurement correctly, what we can find is that the shift that we get if we assume the wrong ordering is in a different direction for the two experiments. And so this gives us a great situation. We can just see which of the two orderings do we find agreement between the long baseline experiments and Juno. And so this gives us a really neat way a new way of accessing the mass ordering without worrying about matter effects. And crucially, it lets us do it using our high statistics muon neutrino survival channel rather than relying on the more challenging electron neutrino appearance channel. Now, another of our key friends, of course, are atmospheric experiments. Here we produce neutrinos in the atmosphere from high-energy cosmic rays. The neutrinos travel through the Earth, and they're picked up by neutrino telescopes. So we have one in the South Pole, that's ICECube. We've got another, which is actually the T2K fire detector as well, Super Kamiokande in Japan. And we've got one on the Mediterranean Sea as well. This is KM3Net Orca. Now, these experiments have very high statistics, and thanks to their enormous detectors, and they're able to measure the muon neutrino survival probability. They can measure the electron neutrino appearance probability as well, and these three experiments now have produced these three really nice plots together that shows the ratio of L over E for the three experiments. Now, in each bin of this, the different experiments have different contributions from L and E, but still when they put things together, you see they're seeing the same oscillation, they're seeing a consistent oscillation that, again, is telling us about the mass splitting and the mixing angle we mentioned earlier. Now, I mentioned T2K and NOVA earlier. We can combine atmospheric experiments with long baseline experiments as well, so we can talk about T2K and SK. Again, I won't talk through this plot right now, but the key thing I just want to tell you is, again, this isn't an easy task. You need to carefully correlate the systematic uncertainties, and together these experiments are able to enhance each other's sensitivities very nicely. So joint analyses are a key way forward for the field. Now, overall, these experiments provide us with data from an enormous range of L over E. They give us precise constraints on these mixing parameters, and they're sensitive to, they really consider oscillations at higher energies over a very long baseline. And so this helps to break degeneracies in theta 2-3. Andre mentioned the octant, this is that, and the determination of the mass ordering as well. So if we put this all together, where are we so far? So now I'm showing you 90% either confidence limits or credible intervals. They're mixed here for the large mass splitting and the large mixing angle as well. And you can see we're really honing in on precision measurements here. The most precise are from T2K, Nova, and ICECube, which is really impressive from ICECube. And we were getting this down to the percent level, as Andre mentioned. Next, I want to talk about CP violation. So we can measure this delta CP parameter, the last parameter that we need to get a handle on. It's to tell us about CP violation. And the leading constraint currently comes from T2K, which gives a 95% confidence limit exclusion of CP conservation and a preference for a maximal value. Now, these plots from T2K and Nova, they're quite hard to compare because they choose different x-axis ranges. So I've just taken the liberty of flipping the T2K plot. I just wrap it over, and now we can compare T2K and Nova. Top one's delta chi-squared, bottom's the posterior density, so compare high on the bottom to low on the top. And what you can see is that the 1 sigma intervals overlap relatively well, but you in the normal ordering, but you find slightly better agreement in the inverted ordering. There is no tension there. So then the actual direct measurements of the ordering. So if you take the experiments without Juno, we're getting to reasonable constraints at the 80 to 90% level, whilst if we add Juno in there as well, you can see that this nice comparison of Nova and Juno that they put together in just a few days following the Juno result release gets to a 94% preference for normal mass ordering. I just want to finish with this to show you how our parameter knowledge has evolved over time, and you can see that really in the last 2 decades we've made enormous progress and really are doing precision neutrino oscillation physics now. Now, we might ask what's next, and I want to also say what does it mean for high-energy physics. So we're honing in on discovering a potential new source of CP violation. Now, importantly, it might be a large source. What you're seeing this plot from T2K here is just a reprojected measurement of the parameters into the Jarlskog invariant, something that gives us the metric for the size of the CP violation. The maximal value is that we could have right now is about 10 to the minus 2. In context, the CKM value of this parameter is 10 to the minus 5. We also can potentially link this CP violation to baryogenesis. We need a model to do this, but if we have, we can put a model together, and even with just the Dirac phase, that's the delta CP we've been talking about, we can construct theories that can explain matter-antimatter imbalance and match the CMB observation. We also are close to determining the mass ordering. This, first of all, sets what we might be able to manage with the next generation of neutrinoless double beta decay experiments we'll hear more about later, and it sets the floor for cosmological mass measurements as well. You have a different sum of neutrino masses for normal ordering and inverted ordering, which is what cosmology can constrain. And then finally, and maybe most interestingly, we can begin to answer, or at least ask, why does the CKM matrix look so different to the PM&S matrix? And is it just anarchy, or is there something more? And there is some there may be some rules. So for example, we see this maximal muon neutrino disappearance. This might imply that we've got our nu3 coupling equally to nu mu and nu tau. If the T2K preference is confirmed in the future of sign delta CP being maximal, being 1, then it would imply a nu tau reflection symmetry. So there may be something to find there. But these are all quite exciting questions. But in order to go and answer these, we need more statistics and smaller systematic uncertainties. And so we need the next generation of experiments. So T2K is evolving. It's an upgraded beam, new near detector, but crucially, its far detector is being upgraded into this enormous hyperkamiokande detector. And then we've also got Dune. Dune provides a whole new neutrino beam, new detectors, and a new technology based on liquid argon time projection chambers. To take a look at these 2 experiments, they're very complementary to each other. Hyper-K is low E, short baseline, narrowband beam. Dune is high E, long baseline, very broadband beam that actually covers 2 oscillation maxima. Hyper-K's first beam is expected in 2028, whilst Dune in 2031. And I just want to highlight those statistics differences. So if you look at, it's not a factor of 2 increase, it's 2 orders of magnitude increase in some channels that we expect from Hyper-K and Dune compared to T2K and Nova statistically. So this is really exciting. Now, just to go through some of the high headline plots quickly, I won't talk through these in detail, but suffice to say that we expect to discover CP violation if it's large quite quickly. So Hyper-K can potentially do this after 2 to 3 years of beams after beam start. For Dune, it will take more like 7 years, but it depends on the exact parameters we choose. Ultimately, Dune will have a slightly tighter reach on the range of the parameters. Then, in terms of the mass ordering, you can see the evolution that you have from different experiments here, and Dune really ramps up incredibly quickly. The matter effect is really large for Dune, and so you expect, even in less than 2 years in some cases, Dune to make 5 sigma statements on the mass ordering. So then I go back to a question that Andre asked as well, and something we might get asked, and it's our responsibility to answer, is why do we need these two experiments to measure those, as Andre mentioned it, 2.5 parameters? Well, I can give you a bit of a boring answer of, okay, there's slightly orthogonal systematic uncertainties, so we increase our robustness, we remove some islands of degeneracy in between the PM and S parameters. But also, I think, as Andre pointed out, we might want to take a step away from considering these as only PM and S measuring machines and think about what they might be able to do to tell us about physics beyond PM and S, beyond the standard model in some sense. So what are we going to do? So Dune and Hyper-K will be able to make high-precision inferences of the oscillation probability itself as a function of L over E. This is potentially sensitive to tiny effects. To remind you, these are 1 GeV scale experiments that are sensitive to neutrino mass differences on the 10m, that's milli-electron volt scale. So these are effectively quantum interferometers, stable over hundreds of kilometers, able to be potentially sensitive to new physics. You can see that since we've got that set up, and you see the improvement in precision we get between the current generation and future generation, you can see statistical uncertainty differences here. We've really got something, I think, potentially quite promising here. Now, in terms of new physics, there's all sorts of physics that we could see. Andre talked about some of these, but what we should be looking for, I think, is for measuring oscillation probabilities between Hyper-K and Dune and seeing that they might depend not on just L over E, but on L and E. New physics will often give an L or E dependence to the oscillation probability as opposed to just the ratio. And I show you an example here of these scalar NSIs, where you see a different change of the oscillation probability at a Dune-like case and at a Hyper-K-like case. So overall, Hyper-K and Dune are really complementary like this. They sit at opposite ends. One's low L, low E, one's high L, high E. We put them together, and we can, the joint measurements between them can be a very powerful test of the PM&S three-flavor mixing paradigm. But it's even more powerful when we combine with the, sorry for the low resolution, I don't know what happened there, with the global neutrino picture. So we can see measurements, for example, from Dune and Hyper-K compared to those of the telescopes like ICHEP, compared to Juno or Daya Bay, all measuring, accessing the same parameters, and we can look for any breakdown there that can tell us about potentially new physics. So to finish, I just want to tell you that, of course, with great precision, potentially, and great statistics comes a great responsibility to keep your systematic uncertainties under control. So let me just say a moment, talk about this for the end of my talk. So, of course, I've tried to tell you that what we want to measure is directly these oscillation probabilities, but what we actually see in the experiment, of course, is the event rate. So to infer the oscillation probability, we need to have these three things under control: the cross-section, the flux, detector effects. Now, if we look to current systematic uncertainties, today we're in a good situation where statistics and systematic uncertainties are similar, ideal for end-of-lifetime experiments, and we can look that the largest one is related to cross-sections. Now, part of this is because we've had fantastic work on the flux side from experiments like NA61, on the detector efficiency side from experiments like Proto-Dune and WCTE at CERN, which have been able to constrain those systematics or provide a credible path to doing so. These cross-sections are more challenging, but overall, still, we see a large uncertainty from these cross-sections, but it's still small compared to our statistical uncertainty, so everything's okay. Now, where do these cross-section uncertainties come from? Now, neutrinos interact with nucleons inside nuclei. It's soft, very soft QCD, and the energy transfer, the scale of the energy transfers is on tens to hundreds of MeV, which is comparable to nuclear physics processes. So we're sensitive to how nucleons correlate with each other inside the nucleus. We're sensitive to Fermi motion, to binding energy, all messy nuclear physics. Now, what this means is we don't just need more data, because we have quite a lot of data with our near detectors. What we need is a new understanding of what's wrong with of trying to improve our theory here. And what this means, unfortunately, is that if we don't do anything, then the current cross-section uncertainties might be representative of what we'd expect for future generation of experiments, where we have 1 to 2% or 3% statistical precision. And so overall, this sets a difficult situation where we clearly need to work to get these under control. So an improved understanding of neutrino interactions is necessary in order to avoid these experiments potentially being limited in the future. Now, there is a way forward for this, thankfully. But it requires a dedicated and deliberate program where we work with the nuclear physics community to be able to improve our models. We benchmark our models against dedicated lepton nuclear scattering measurements, both electron and neutrino scattering, and even hadron scattering too. We feed what we learn about into our near detector fits, and this whole thing is iterative. We improve models, we test models, we improve models. The issue is this process can take, and it has taken in the past, years to complete. And so this is something we need a dedicated community effort on now, and it is growing, but it will be important for the success of these experiments. So overall, I want to finish by telling you about a possible timeline for what you might expect in the future. So I'm optimistic, and I say that, okay, CP violation is large, and the mass ordering can be determined, and so we expect to see a combination of experiments telling us the mass ordering, then Hyper-K telling us about CP violation, Dune providing a single experiment verification of the mass ordering. And then we go forward from there. And we might find that, okay, we go to 2035 and we see that Dune and Hyper-K have some disagreement. And we look a bit closer and we find, okay, it was just a cross-section mismodeling. We've got some work to do. But I hope that as a community we can come together, we can get all of these systematics under control. So towards the end of these experiments' lifetimes, where we make comparisons of the inferred oscillation probabilities, if they're different, we can be sure they're different. We can be sure there's some interesting explanation beyond standard model physics and be in a position to be able to really test three-flavor neutrino mixing paradigm. So I think I'm more or less out of time there, so I'll leave you with my conclusions. Thank you very much.
Thank you very much for this really nice talk. Questions there and also there.
Okay. Thank you. This was a great talk. Question about your timeline on slide 50, 51, 50. Or maybe you can just stay here. But right now I think there are 2 detector modules under construction, and your numbers presumed 4 of them. What happens if we don't? How would the timelines for both mass ordering as well as delta CP change if we have only 2 modules?
So in terms of mass ordering, it makes effectively no difference. Dune is a staged experiment in any case. The plan was always 2 modules, then 2 more modules. So the mass ordering sensitivity remains there entirely. Effectively, if you lose 2 modules, it just means that it takes a longer time to be able to reach the same precision. So it will increase the timeline needed to be able to get precision measurements. I should point out that in terms of the PM&S measurements, it's Hyper-K that would make the statement, likely to make the statement about CP conservation, rejecting CP conservation first, and that is obviously unaffected. So in Dune, and I will also point out that whilst Dune, the staging approach means that the second 2 modules might come later than originally planned, the beam ramp up in power comes earlier than maybe planned, so the current plan remains very much what I've shown you here. But of course, less detector mass means less statistics, means it will take longer.
Thank you.
Sorry, I missed my... So I have a question regarding the compatibility between NOVA and T2K in the determination of delta CP. At the beginning, you show a slide that seemed to suggest that inverted ordering lead to full compatibility, but then at the end you concluded normal ordering was preferred, and I didn't understand why. So then, could you comment on that?
Sure. So when T2K and NOVA do their joint fit, they actually find a very, very weak preference for the inverted ordering. It's 50-something% because they agree slightly better in the inverted ordering. But when you do the T2K NOVA joint fit and you ask, okay, what is the Bayes factor when I look to my normal ordering hypothesis, it's good. So on the slide I showed you before, you could see that there clearly was preference in the inverted mass ordering, but you still have agreement in the normal ordering. And the global neutrino oscillation picture still points you towards the normal ordering. So you would say that the T2K NOVA, so where you see slightly better preference for the inverted over normal for T2K NOVA right now, it's compatible with the statistical fluctuation.
I see, but there seems to be no agreement for normal ordering. The preferred regions were totally inconsistent. So
No, they overlap.
Very broad. Okay, very good. So
They do overlap. It's about, if you take the 68% confidence limits in the plot I was showing you before, this 68% confidence limits for the 2 experiments overlap.
Okay.
And as I said, when you combine them, the Bayes factor is good.
very good, thank you.
Question here?
Well, thank you very much for your very interesting talk. I think that in the first line, Juno should be mentioned in the first line.
Juno.
Juno, yeah.
Sure. The next speaker will tell you much, much more about Juno, and you can, yeah. There is the dedicated talk on short baselines.
We have one question there.
Hello.
Thank you for the talk. I just want to make sure I understand. If I understand you correctly, no matter what Dune does, there will be 7 years after the CP violation of 5 sigma is established in 2030 in the Hyper-K. Is that correct?
So that was assuming maximal CP violation. Of course, if we change the PM&S parameters, there are cases in which you would expect, so Dune can exclude a slightly larger range of different, so the amount of CP violation depends on the delta CP parameter that we have. If we have something that's very close to the edge of sensitivity of Dune and Hyper-K, then it could plausibly be Dune could get there first. But that would require the parameter to take a special value. Now, the key thing is, I think the motivation very much for having both experiments is physics beyond PM&S and looking for inconsistencies, like I mentioned before. So in terms of PM&S observations, Dune will certainly be the one to give us of the two experiments there. It is the more likely to be the single experiment to tell us the mass ordering quickly, whilst Hyper-K is the more likely one to tell us about CP violation. But in the far future, you can combine them to tell us about beyond PM&S physics.
Now here.
Thank you for a very nice talk. You argue that current systematics are already larger than Dune Hyper-K projected statistical errors. Concretely, which single investment like near detector capabilities, electron scattering data, or nuclear theory buys the most uncertainty reduction before 2030?
That's a wonderful question. Thank you very much for giving it to me. So I think the theory side needs support, and I think right now, if we don't build something totally new, the theory side is what will get us there. Having movable detectors is also really important. That helps. That might help escape us from some of this, though it still needs to be demonstrated. And finally, I'd like to mention this idea of building a tagged neutrino beam, where you know the neutrino energy event by event. It gives you a much nicer way of being able to disentangle cross-section effects from any other effects. That I would very much like to see that happen to help resolve this issue.
So, more questions or no more questions? Thank you again, Stefan.
Thank you very much.
So now we welcome Zay1U to talk about neutrino properties from short experiment now.
Okay. Yeah, let me try my microphone. It's good. So it's my great honor here to present the neutrino properties from the short baseline neutrino experiments. So as talked by the two previous presentations, there are many important questions in the neutrino physics, and the neutrino oscillation is a sensitive tool to study these questions. So in this decade, determine the neutrino mass ordering is critical. So it will help us to reduce the difficulties and to determine the CP violation phase from the long baseline experiments. And it will narrow down the results from the neutrino-less double beta decay experiments, and also build the synergies with the astroparticle physics and the cosmology. So among the neutrino oscillation experiments, the reactor neutrinos is a great tool from the discovery 70 years ago for neutrinos, and then to the measurement of the C212 at Cameland, and the C213 measurement at Diabei Reno double show, and now to the mass ordering determination. So we studied the disappearance of the reactor neutrinos. So we have the clean disappearance channel, and it is independent of the matter effect and the unknown CP phase. So among the reactor neutrino experiments, the southern China is a great place to carry out this kind of experiments in the Guangdong, Macau, Hong Kong, Great Bay Area. There are many hills in this region, which means it's more or less easy to build an underground experiment. And also, there are multiple nuclear power plants here from Daya Bay. It's a little less sensitive, but anyway, from Daya Bay here, Fossil 1-3, and Juno there, the Jiangmen and the Ground Neutrino Observatory, which sit at the equal baseline to the Yangjiang and Taishan nuclear power plants, which provide Earth the sensitivity for the neutrino mass ordering. So this is a quick show of the reactive neutrinos, which is the strongest artificial neutrino source over the world. They were produced in the beta decays of the fission fragments from the 4 major fissile isotopes. And their energy locates at the MeV region, less than 10 MeV usually. And they can be detected by the inverse beta decay easily in the scintillator, in the water, and other targets. And after the IBD reaction, there will be a positron and a neutron. They will form a correlated signal, which can improve the signal over background ratio by several orders of magnitude. So in the past 2 years, a great milestone is the operation of Juno. So 2 years ago, in the ICHEP 2024, in the review talk by Petro, it was said Juno is expected to data taking in about 1 year, and this was achieved. The water filling of the Juno detector started in the December of 2024, followed by the scintillator filling, which finished in the August 2025. After that is the stable operation, and the first results come out only with 59 days of data, and published this year on Nature and the Chinese Physics Day. So with more than 200 of days data, the normal mass ordering is favored. Let me go through Juno first. To have the neutrino mass ordering sensitivity, so Juno should have a 20 kiloton liquid scintillator detector and 3% energy resolution at 1 MeV. Compared to, for example, Cameland or Daya Bay, the previous experiments, Juno should have the substantial improvement in the PMTs, in the liquid scintillator, and even in the installation. And these technical difficulties are eventually overcome. The largest acrylic sphere was built over the world. 20 kilotons, very transparent liquid scintillator was filled with attenuation length longer than 20 meters. The scintillation photons were detected with the innovative PMTs, 20-inch, both from the MCP one and the diode ones. The MCP ones, the efficiency is more than 30%. And eventually, with the very careful installation procedure, the 75% coverage has been achieved. There's only 3 millimeter clearance between the 20-inch PMTs. Yeah, very difficult. Yeah, this is the photos during the installation. That one is the, let me see. Yeah, this one is the acrylic vessel is going to close. And the acrylic vessel supported by the supporting bars and veiled by the PMTs. And the PMTs and the supporting bars were supported by the stainless steel structure. And here the workers is inspecting the acrylic carefully. And this is the last photo before our water filling. All the equipment has been installed in the detector. The Juno detector is quite clean. Due to the large mass, it is very difficult to recirculate for cleaning of the liquid scintillator. So from the very beginning, the low background control is critical. So from the simulation of the background budget, carefully screening and radiopurity control of the raw materials and the production handling, etc. And during the filling of the liquid scintillator, all the joints were carefully checked and protected by nitrogen, and the inner surfaces were carefully washed and cleaned. And in addition, the inner surface of the acrylic vessel is protected and cleaned right before the filling starts. So the current background level fulfills the requirements in the urea and thorium contaminations for the solar and reactor neutrino studies, and also good enough for the future neutrino-less double beta decay upgrade. Yeah, this is a golden reactor neutrino experiment in the detector, where you can see the prompt signal from positron, and the delayed is the neutron capture. And the energy response is critical for the neutrino oscillation measurement. So in the Juno detector, the light yield was measured to be more than 1,600 for the germanium source, and we can also see a good agreement between data and Monte Carlo. So the non-uniform light yield along the radius was corrected using the comprehensive calibration and reconstruction efforts. That is, the residual spatial non-uniformity and time instability for the reconstructed energy is less than 0.5%. And also, the nonlinear energy response of the liquid scintillator is calibrated to a precision better than 1%. So the most critical one, energy resolution, currently it is about 3.5% for the 2 gammas from the germanium-68 source. So it is slightly worse than the expected 3.1%. But if we look at the different particles, for example, alpha, with the similar reconstructed energy, the resolution is much better, 2.9%. So it means Juno will carry out better Monte Carlo simulation, more calibration, better reconstruction, and extra to further improve the energy resolution. For the reactor neutrino events, as I said, they were selected according to the coincidence between the energy of the prompt and the delayed, and also the time and the space. The current background to signal ratio is 1/9, good enough. And the current largest background is lithium 9 from the cosmic muons passing through the detector, 1.4 per day. Actually, it was 80 per day before our veto. So thanks to the very good muon track reconstruction using transformer and deep sphere techniques, and also the good training data from the top tracker detector, the lithium background was suppressed much. The IBD efficiency, 74%. I think several percent improvement is expected. So the measured neutrino rate is consistent with expectations. And this shows the measured spectrum of the reactor neutrinos plus the background. And the big discrepancy with the prediction is the theta-1-2 oscillations. And the table shows you the detailed of the background, the efficiency, the uncertainties. I will not read it. Eventually, the spectrum was fit under the 3 neutrino oscillation framework, and also with constraints from the near detector spectrum from Tau and Diabase. Additionally, the gel neutrino rate was left free in the fitting now. So the left plot shows you the 2 parameters, theta-1-2 and delta-m21 measurement by Juno. And you can see the 2 measurements using 55 days of data and 207 days of data. They are consistent, precision keeping improving. So the breakdown of the error budget shows you that although the statistics is dominant in the 2 parameters, the systematics becomes more and more important. So the Juno collaboration is improving the important background and detection efficiency. And to the delta-m31, the more interesting measurement. So the top plot is showing you the Juno-only profile on the delta-m31. Due to the statistical fluctuations, there are multiple minima in the current measurement. And with more and more data online, Juno will select the correct minima in the future. So currently, we use the Diabase final oscillation measurement on the delta-m31 to select the correct minima, as you can see in the dashed line. And the Feynman-Constant method was used to build the 1 sigma range of the oscillation parameter, and eventually you can see the delta-m31 were measured to 1% precision. And additionally, from the synergies between the short baseline reactor neutrino experiments and the long baseline accelerator neutrino experiments, we got the sensitivities on the neutrino mass ordering. That is, you can see in the normal ordering, the measurement from Diabe, from Juno, and from the long baseline experiments, they align well. But then to the inverted, they diverge. The delta chi-square is 4.86. To convert the delta chi-square to the significance, in the frequentist approach, the Feynman-Constant method was used in considering the influence from the unknown CP phase. And the 2.1 sigma favor on the normal mass ordering was obtained for the one-sided Gaussian distribution. And also the Bayesian analysis was performed, and the normal mass ordering is favored with a Bayesian factor of about 10. Okay, that's almost all for the Juno. So currently, the three oscillation parameters, theta12, delta M21, and delta M31, the precision is dominated by Juno now at 1% to 2% level. So the Juno is under the stable operation now, and with more and more data coming, the precision will go to 7% level soon. Yeah, let me go through the other aspects in this field. First of all is the theta13, which is the dominant experiment, also the reactor neutrinos. That is the Diabe, Reno, and the double show. So actually, there's no new updates on theta13 since the summer of 2024. However, a new publication this year indicates that the difference between Diabe, the NGD, and NH analysis, which is the neutron captured on gadolinium, hydrogen, the difference can be explained by the new Bismuth 214 background identified by SNOWPLUS first and then Juno. And considering the new background, the theta13 measured by Diabe NH analysis will increase to the similar level of the NGD analysis, well consistent is expected. And the Diabe collaboration is finalizing the analysis. For the SNOWPLUS, they finished the scintillator filling 4 years ago, and they observed reactor neutrinos from the reactors with an average baseline more than 600 kilometers. So they were able to see the multiple oscillation peaks here from the theta12 oscillation. And also they have the background from the RFN, and they also observe the gel neutrinos. They report the solar and reactor neutrino fit to the two oscillation parameters in the same detector. The fitting results is consistent with the global results. So actually, there's another experiment, silver K, gadolinium. They also observed the reactor neutrinos in the gadolinium-doped water Cherenkov detector. Actually, I updated one slide, but it seems the slide was not updated. So I will quickly mention it. And so another topic in this field is the very short baseline reactor neutrino experiments. That is, if you place a neutrino detector close to the reactors at meters to tens meters scale, and one can measure the reactor neutrino flux well. So you can see in the history there's more than about 20 experiments. Their measurement of the neutrino flux are well consistent, but there's a 5% discrepancy of the rate compared to an updated theory prediction in 2011. Yeah, this triggered EV scale stereo neutrino explanation, and also followed by more than 5 very short baseline experiments to search for the L/E feature for the EV scale stereo neutrinos. But now we have the feeling that the EV scale stereo neutrino explanation is not favored. And that is, in all the experiment, they observed a bump at 5 MeV which cannot be explained by the predictions. And also, field evolution studies by Diaby, Reno, and Extra, they indicate the urium-235 is the main contributor of the, namely reactor antineutrino anomaly. The neutrino 4 and the gallium, the two experiments, they are allowed reasons for the stereo neutrinos. Most of the reasons had been excluded by the other experiments. So a new apparatus online this year in this field is Juno Tau, a satellite detector of the Juno experiment. Its aim to precisely measure the reactive neutrino spectrum at a very high energy resolution. So it uses the gadolinium-loaded scintillator running at minus 50 degrees with the silicon PMs. In this way, it obtained about 4,000 photoelectrons per MeV for the light yield. And the energy resolution is better than 3% better than Juno. Use about a half a month of data. And you can see here, there's a reactor off period for the background and a reactor on period to measure the spectrum. A beautiful reactor neutrino spectrum was measured with the highest energy resolution. So the comparison shows with the model shows the good data and prediction agreement, and this spectrum has been used as the high resolution constraint in the Juno oscillation fit. So the last one I would like to mention is the seventh, coherent elastic neutrino nuclear scattering, and which is a new tool to measure the reactor, solar, supernova, and decay at rest neutrinos. It can test the electroweak physics in the standard model and also search for the non-standard interactions. So there's many experiments you can see. The coherent experiment, they provide the measurement on the seventh cross-section of many targets. And their measurement agrees with the standard model well. The Conus Plus found the reactor neutrino 7th at 3.7 sigma. And also, as you heard yesterday, the dark matter experiments, they report the 7th from the boron 8 solar neutrinos at different significance levels. So now there are more than 20 experiments under construction, commissioning, and running, also include Coney from here. Okay, I think this is a summary for the short baseline neutrino experiments, and in particularly the reactor neutrino experiments. 4 oscillation parameters has been measured with the highest precision. And 3 of them, the precision will keep improving with the more and more data from Juno. And the sub-percent level measurement is expected soon. For the method ordering, currently from the synergies between the short baseline and the long baseline experiments, the normal method ordering is favored more than 2 sigma. And Juno will improve its energy resolution and to further enhance its sensitivity on the method ordering. So by 2030, maybe I hope we already have a definite answer on the method ordering, or maybe we have some hint or even evidence for the CP phase. The new physics, for example, the EV scale stereo neutrinos become weaker and weaker. Yeah. Okay, let's stay tuned for more exciting results. Thank you.
Okay, do we have any questions?
Thank you for the very nice talk. I'd like to discuss this June Tau, because my question is, beyond constraining June, can Tau's fine structure settle whether the 5 MeV bump is a nuclear physics flaw in the prediction of the uranium prediction? And also if it does retain any sensitivity to electron volt scale sterile neutrino oscillations at its baseline.
Yeah, it's a great question. Let me answer one by one. And first of all, for the 5 MeV bomb, tau, it needs more statistics to investigate whether it comes solely from the urium or comes from both the urium and the polonium. And I think from the diabetic previous analysis, the contributions from the 2 isotopes are more or less equivalent for the bomb. And the second question is for the search of the stereo neutrinos. I remember there's already some sensitivity studies within the collaboration. For the EV scale, I think the most sensitivity distance is 10 meters to 20 meters, and to the 44 meters baseline, and it might be sensitive to the, for example, 0.1, 0.3 EV scale, something like that. Yeah, thank you.
Any other question? Murilo?
Thank you for the nice presentation. So on your slide 19, when you show the Juno multiple minima, it seems to me maybe that's something that you have discrete differences between the minima. Is that expected, or is it something natural from the fit, or is that something that you expect to happen?
This is expected to happen due to the limited statistics. Maybe with 2 years or 3 years data, Juno can select the right minima. Yeah, and we can repeat this from the toy Monte Carlo experiments. Yeah.
So let's thank the speaker again.
Yes. Thank you.
We have an announcement now.
So we have the photo now. It's going to be outside the building, but right in front. So let's gather there together now, but in a controlled way, yes. But we need to get there as quick as possible. Thank you.